Thank you, the hosts and participants, for welcoming me here. And I thank all the organizers and Dr. Vivek and Dr. Karthik for this opportunity for sharing some research ideas with the peer community. So today we'll be discussing a few things related to solar PV potential estimation in the context of planning of a renewable energy scenario for a particular region. So this is very pertinent in terms of the escalating ambitions of having a much larger share of renewable energy in the Indian power system and the power grid. And also it's very pertinent with respect to the topic of the present e-workshop on the operation and planning of distribution system and microgrid. So before we start here, let me just ask a question to the participants that when we say potential estimation for any given technology, in this case, we're talking about solar PV. So, what do we understand by this term potential estimations? Can someone say their ideas, what they feel or what they take when you say potential estimation? You can write in the chat box if someone would like to share. What do you understand by potential estimation? Uh, so we have one reply from a participant, and he says that Mr. Prasad Ganevar, he says that what amount of energy would be available, estimating that for use. Very true. I mean, when we talk about potential estimation, another participant also has given estimation of utilizable energy, estimation of PV rating. Okay. So the, different people have given few replies. So before we go ahead on this thing, let me just make it clear because this terminology sometimes is confusing and we should be clear when we discuss about these things. Another reply is there. Potential estimation is how much solar energy can be captured per square feet. Yeah, thank you so much. So most of you, what you are pointing out to is a correct answer, but let's classify it further. And most of the replies which we have got, they are mainly talking about the technical potential. So we should be clear when we say about the potential of the technology, there are different stages to it. So as technologists and engineers, we typically tend to look only at the technical aspect. But then there is always more to the technology when we talk about it in terms of the implementation on ground. Just the technical potential won't do. So there are three stages basically. First is the technical potential. So technical potential means given the constraints of the technology and the resource availability and the other technical constraints, how much of energy output do we expect to come? So like for example, suppose I have some, let's say 5 acre plot, and I want to see that, okay, in that 5 acre plot, how much of solar PV I can install, and accordingly, how much of electrical output can I generate on a daily basis or in an annual terms. So that is just the technical potential, given that, okay, what is the available technology and what is the available solar resource. Based on that, and what is the land area, we can say that, okay, this is the available potential of solar PV. But then as we can understand, this will be I mean, it will also depend that what is the investment I have to make for this, and what will be the return which I'll get out of that particular investment. So everything which is the technical potential doesn't really manifest as the actual implementation. Why? Because there comes the other threshold, which is the economic potential. So even if there is a technical potential available for a given technology and technically it is viable, but another thing which needs to be looked upon and which people definitely consider before implementing something on ground is the economics of it. So how much is the investment which I'll have to make? What will be the return which I'll get from that investment? What is the expected rate of return? Whether it is having a net positive net present value or not? Those constraints, economic constraints, they come into picture. So what will happen practically is that of the total technical potential, lesser fraction of it will be what will be actually economically viable. And then again, even if something is economically viable, doesn't always make sense that people will go for it. So even if it is making economic sense, suppose, I mean, because again, the decision to go for a renewable energy technology or a sustainable technology is usually these technologies are decentralized in nature. So, and especially if we talk about solar PV or rooftop solar PV to be particular, then it is completely decentralized in nature. And the decision of a particular building owner, whether they want to install that rooftop solar PV on their building or not, is not only dictated by the techno-economics, but also comes into picture the behavioral aspects or the social aspects, the policy constraints, and the other, the practical constraints which come into picture. So that further reduces the achievable potential, and that's why what we get finally on ground is even lesser, and that is what the is known as the achievable or the market potential. So again, there is a reduction factor which comes into picture there. And this third one, the achievable or the market potential, this will be having, there will be diverse factors which will come into play here. So it can be behavioral aspects of the consumers involved. It can be the social aspect, the openness to new technology at the social level. It can be the government policies and the uncertainty or the certainty in the policies. So all those things will come into picture and will actually reduce the actual achievable thing on ground to a lesser fraction. So when we say potential estimation, we can be talking about any of these levels, whether we can be talking at the technical level or at the economic level or at the final achievable or the market potential level. And all these things are pertinent problems and which need to be addressed. But in this today's talk here, we will be restricting ourselves to only to the technical potential, because the flavor of the problem changes as you talk about the different levels. So in this today's discussion, our focus will be mainly on the technical potential. So with that thing, this figure here gives you some idea about in terms of the numbers when we say how much how things change. So this is from one review paper which I published around 2 years back, 3 years back almost now, 2018. And we looked at the literature for the growth of renewable energy technologies in the country, in India. And specifically, we looked at four technologies: solar PV, small hydro, wind, and biomass. So, and then I mean, at that time, solar PV was still new because this data which went into this study was typically up to 2016 and all. So the technology solar PV was much nascent at that time. So we didn't have a larger database. We had only like 5-6 years data from 2010 to 15 or 16 onwards. And but then there were different trends and extrapolations which people had made, and we studied those things and tried to fit some models to that. And what we found was that the green curve here, which you see, is the what is the theoretical potential or the technical potential of solar PV in India, as estimated by MNRE. So the Ministry of New and Renewable Energy of India, they have estimated that the total technical potential of solar PV in India is roughly around 750 gigawatts. That's a very huge number, and as we know, the government has this National Solar Mission, as a part of which we are having a target of 100 gigawatt peak of solar PV installation is being targeted by 2022. And that's still a very small fraction, as we can see, of the total technical potential. And then how much of it can be realizable or the realistic maximum potential, that is, you can see here in this graph, on this graph by this red curve. So that is just an estimate again, but taking into account different other practical considerations, not just the techno-economics, but also the market penetration and other social behavior patterns. So that is almost half of what is the theoretical maximum. So that type of reductions will we can probably envisage for any new technology. That however even if the technical or the theoretical potential is huge, the actual what is achieved on the ground is usually a lesser fraction due to these different considerations which come into picture. So with that background, now we'll be talking mainly about the technical potential and the estimation of the technical potential of solar PV. But before we go ahead to that main discussion, first of all, we should also become clear about whether what is the units in which we are talking about. I also like when I asked this question in the beginning of this talk. So most of you replied in terms of energy, but someone also wrote about PV rating. So that thing rating, usually we have the rating of the PV in terms of the power units, kilowatt peak or megawatt peak or megawatt peak. But energy, as we understand, usually electrical energy, we talk about in terms of kilowatt hours or megawatt hours. So both of these are very important and crucial to this discussion, and why we'll come to that shortly. So just a review of some of the basic concepts. I hope everyone is aware about these concepts, but still, for sake of completion, we'll just go through this quickly. So when we say the capacity of a solar PV installation, the rated capacity, we talk in terms of the rated power capacity. And this is, however, as we understand, the PV rating is defined under the standard test conditions or the STC conditions, as they are called. And they comprise of three conditions. One is the cell temperature. So the temperature of the solar cell, please, we should be careful here. We are talking about the cell temperature, not the ambient temperature, or neither the panel temperature. The cell temperature basically should be at 25 degrees Celsius, and the irradiation falling per unit area on that solar PV panel should be 1000 watt per meter square. And the air mass, which denotes the type of solar spectrum, because as we understand, when the solar radiation travels through the Earth's atmosphere, there are different effects which it goes through due to the atmospheric particles which are present. So there is some attenuation, some absorption, some reflection. So this the effect of atmosphere will be different depending upon how much is the path length of the radiation through the atmosphere. So different path lengths will have different effects, and to standardize the discussion on solar PV efficiency and rated capacity, the standard has been taken as AM 1.5 spectrum. So with these three standard test conditions, what we get the PV output, the power output, that is defined as the rated capacity of the solar PV installation. But as you understand, practically speaking, the practical considerations, the practical the ambient conditions will be usually very different from this, because this air mass AM 1.5, this corresponds to a particular solar incident angle, which will happen maybe just once or twice a day. Other times it will be different, and then irradiation of 1000 watt per meter square, again this is almost the maximum value which we receive on ground on the earth's surface. So across the year, for most of the time, for most of the seasons, and also even in when the value will be different from this value of 1000 watt per meter square. And even when we have the cloudless sky and the sun is shining brightly, then also this value of radiation will only be achieved maybe for a few hours in a day when the radiation is peaking. So practically speaking, for most of the year and for most of the time across the year, this value of irradiation will be lower than this. And the cell temperature, if we talk about in the context of a tropical country like India, so the temperatures, as we understand, the ambient temperatures themselves are quite high, and for many times of the year, this can be 25 degrees Celsius or higher, the ambient temperature itself. And then whatever is the ambient temperature, the cell temperature is always higher by a particular amount due to the ohmic losses, as we understand, because the solar cell, there are some ohmic losses, and the when the current is being generated, and due to that those I square R losses, the temperature of the cell rises further. So most of the times, the ambient temperature in tropical countries is also high. So the cell temperature is much higher than this standard value of 25 degrees C. So, and ultimately what it results in is that when the irradiation is lower, the output of PV is low, And when the temperature is higher, for every 1 degree Celsius rise above this cell temperature value, again the PV output drops by a particular fraction. So practically speaking, what we get as what we call as the rated capacity of the solar PV installation, that is typically close to the maximum capacity. It's not really the the actual what you get out at most of the times. Rather, this is the maximum what we probably can expect. So, so as we can understand, if we just plot the graph of solar PV radiation across a day, so when you have a cloudless sky and the high radiation is there in a particular season, at that time maybe this peak value will be close to 1,000 watt per meter square. But even in this season, for other hours, the values will be lesser. And if you have cloudy sky and monsoon weather or things like that, then even this peak might be much lesser. So it will be way below 1,000 in those seasons. So practically speaking, what we get is that most of the around the year, this value is much lesser. The output of PV is much lesser. And that's why when we define the PV rating, you will always see that there is this symbol P or a subscript P which comes with the power units. So it is watt peak or kilowatt peak or megawatt peak. And this P indicates that whatever we are calling as the rated capacity of the solar PV installation is actually the peak capacity. And most of the time, it will actually be lesser than this output. So that is one thing we need to be very clear about when we talk about the solar PV. And another thing is that when we say that, okay, how much is the installed capacity? So this I see here, how much is the actual installed capacity if we say. So this equation here is a very simple equation, just in terms of the the basic things. What are the constituents here? So one is the irradiation, what is incident, watt per meter square. So if we take the rated value, this is 1,000 watt per meter square. Then area A is the active area of the solar PV panel. The solar cell area, which is active and which is converting the radiation into the electricity output. So typically speaking, this is the total incident irradiation. So irradiation I watt per meter square multiplied by how much is the active area A. So I into A, this gives the incident radiation. But then this gets multiplied by the efficiency of the PV panel, rated efficiency, eta PV, and then the efficiency of the power conditioning unit, eta PCU. So practically speaking, this equation sort of gives us the idea about the installed capacity. But again, I'll emphasize on this point that this installed capacity is typically the peak value due to these above, the ambient conditions, the irradiation being less than 1,000 for most of the time of the year, and the ambient temperatures usually in tropical countries like India being higher than the rated temperature. So this is something which happens here, and this is something which is a thing of concern with respect to the solar PV output. And that's what it says here, that as we understand, the radiation around the year varies greatly, and for most of the year, it is well below 1,000 watt per meter square, and the cell temperatures are higher. So therefore, the actual energy output from the installed capacity is much lesser. So that is something which is very, very important and crucial when we talk about solar PV, and also specifically when we compare solar PV with the other generating options. Because this reduction factor which comes into picture due to these considerations or the constraints of the technology, these are very stringent, you can say. So actual energy output what we get from solar PV installation, that is defined by the specific yield. So when we talk about the energy output, we talk about the specific yield, and this specific yield is given by the units of kilowatt hour per kilowatt peak per year. Okay. So as we understand, kilowatt hour is the electrical energy unit, and so for each kilowatt peak installation of solar PV, how many units of electrical energy output do we expect in a year? That is what this specifically indicates. So this is a very interesting unit because this is not efficiency. Please note, efficiency is different, because efficiency, when we say efficiency, is the energy output by energy input. But here it is not energy output by energy input. Rather, here this specific yield is you can say it's synonymous or analogous to the term capacity factor or the plant load factor. That how much is the installed capacity, how well it is being utilized across the year. So if you have X kilowatt of installed capacity, out of that X kilowatt, how many units of energy are you able to extract in a year? That is what this specific yield indicates. And it's similar in nature to capacity factor or the plant load factor. So before we go ahead, a quick question again is that what can be the theoretical maximum value of this specific yield for any generating technology? Can someone say? Not for solar PV. Solar PV, I'll come to just in a while about the number for solar PV. But if let's say I talk about any other technology, any generalized power generation technology, suppose you talk about a coal-based thermal power plant or any other technology, what can be the theoretical maximum value? How much maximum value of a specific yield can you expect for any power generating technology? Can someone answer quickly in the chat box? Any idea for anyone? So it's quite simple if you see. So we are talking about, let's say if you have 1 kilowatt of installed capacity of a power generating technology. Now this 1 kilowatt which we are having, suppose I run this 1 kilowatt of installed capacity at its maximum capacity across the year. So for all the 365 days in a year and for all the 24 hours per day, right? So that will give me the theoretical maximum value if I run the capacity at its full capacity for across the year, all the hours, all the days in a year, and for all the hours in each day. So what we'll get is maximum theoretical output possible is 8760 kilowatt hour, right? So that is the theoretical maximum value which we can have for any power generating technology. But this is theoretical thing. Obviously, for any practical power plant, you will have some downtime. So, at least the maintenance downtime will be there. So it will be lesser than this always. But this is the theoretical maximum value. So if you have a good coal-based thermal power plant and which is in good running condition and also it's economical to run, economically viable, and it's a base load plant, then you can have up to 95% of this value is achievable. So those type of numbers are possible. But when we look at the solar PV, this value is in this range. So typical values of specific yield for solar PV is very low, as you can see, around 1200 to 1700 kilowatt hour per kilowatt peak per year. So for each kilowatt of solar PV installed, you can expect this many units of electrical energy output in a year. And this too is these are numbers for the tropical countries like India. And when you go to European countries or other countries where the solar radiation is low, these values are even lesser. So even in India, there is a range, as you can see. So typically the western and the southern part of the country is much richer in solar radiation, and there we can have values close to this, up to 1700 or even 1800 units per kilowatt peak per year. Whereas the eastern and the northern part of the country is having much lesser radiation, and there the values will be in the lower range of this bracket, maybe 1200 to 1400 units. But so these are the values for a tropical country. If you go to European countries where the solar radiation is lesser, then these values are much lesser, way below 1000 units, also 900 or even lesser. So that type of thing is inherently, you can say this is an inherent disadvantage which comes with the solar PV technology because of the nature of the solar resource itself. So as we understand, the solar radiation is having this type of a triangular type profile, parabolic profile in the day, and then across the year, this peak of this parabola also changes. It shifts up and down. So this is something which is important. So when we talk about solar PV potential, power and energy is not having a one-to-one correlation. That is something which I want to drive home. So therefore, because for any other technology, when you say the potential, then just talking about the power might be sufficient. But when we talk about solar PV, due to these considerations, because there is the energy which you can draw out of a given capacity of solar PV will be different depending upon the locational constraints and the ambient conditions. That's why when we talk about solar PV, it's important that we specify both the power and the energy. And therefore, as you can understand, is that these things, when we say these type of graphs which you see many times, and like MNRE also releases data like 750 gigawatt and all, or you have the National Solar Mission of 100 gigawatt. We should always take that with a pinch of salt, because we understand that this 750 gigawatt of solar or even 100 gigawatt of solar doesn't actually mean it's not really equal to 100 gigawatt of coal in terms of the energy output. The energy output will be different, and it will be different depending upon several locational and local constraints. So those things are important and must be taken into consideration when we talk about solar PV. So with this background, now let's come to our main discussion here in terms of the solar PV, the technical potential estimation for solar PV. So as we understand, when we say, as I mentioned a few minutes back, that the technical potential is basically the how much is the theoretical maximum output possible given the technology constraints and the resource constraints and the whatever are the practical constraints in terms of the technology and the resource and the technical constraints. So in this case, when we talk about the solar PV technical potential, as you understand, there are two types of solar PV installations. One are the utility scale solar PV, which is the large megawatt scale solar PV parks which we see across the country now. There are several of those. So these are mostly greenfield projects, and a project developer usually once the project has been awarded, they procure a particular in a particular area, they procure some land and put up a lot of solar PV installation on ground. And usually that is a shade-free area. There is no constraint of shading and all, and they just have that solar PV installation, and whatever is the energy being generated with appropriate power conditioning units, inverter and transformer and all, it is fed to the grid. So when we talk about this utility scale solar PV or the solar power parks, then the technical potential estimation is not a concern, because it's a shade-free area and it's a greenfield project. So it's just simple arithmetic, just by the simple equation which I put here, just by something of this nature, simple equation like that, we can estimate the potential of solar PV for this for the utility scale solar PV. But the problem is more acute in case of a rooftop solar PV. And why it is acute? Some of the reasons are given here. Because as we understand, rooftop solar PV, first of all, the constraint is on area available itself, and the area available on a rooftop for solar PV generation is severely constrained due to the first of all the roof area limitations. So on the rooftop there will be different other structures also which might be there. So you might have a water tank, you might have some other the staircase and other things like that, which will eat up some area. You might need some area for let's say putting up a solar water heater, or you might need some area for drying the clothes, or different other utilities and water pipes and things like that. So those things will eat up some area. That is one thing, roof area limitations. Then there is a shading problem, which is predominantly there due to the adjoining structures. So the adjoining structures on the same roof, or maybe the nearby roofs, nearby buildings, maybe trees nearby if the building is not very tall. So rooftop solar PV, how much is the potential available in a given region or in a given city? This is not really very straightforward problem, and this is where the challenge is. So the discussion here in today's discussion will be mainly about the strategies for estimating the solar PV potential in terms of the rooftop solar PV potential. So this is something of concern, and because also we understand this is why it is important, because as we understand, most of our urban centers, the cities, are huge energy guzzlers, and they have huge and growing energy demand. And it would be always advisable and desirable that if we can at least, if not fully, if we can meet a portion of that particular demand of the urban area from the rooftop PV itself, then that will sort of ease the requirements on the other generating options. So that's why rooftop solar PV is of interest, and people are concerned about having a much better share of rooftop PV. So when we talk about this rooftop PV potential estimation, this is a little, you can say, complex problem because of the reasons we discussed before. How to estimate the rooftop area, how to get the shade-free area, and how to extrapolate that in terms of the overall potential for a region. Those are sort of complex problems. So there are no direct methods for estimating the rooftop PV potential. And the choice of the suitable method will always depend upon the data availability and also the availability of the advanced technologies which can be used for this exercise. So accordingly, there are a lot of variety of techniques which are available and methods which have been discussed in the literature. So we'll look at some of these. So there are a lot of methods which have been discussed, and this listing here gives you an idea about some of the common methods for rooftop solar PV potential estimation. So sometimes if the building stock data is available, that is nothing better than that. If you have the detailed data, if you're talking about a particular city or a region, and you have all the data about how many buildings are there, what is the shape and size of each building, and the spacing between the buildings and all. So if you have the detailed building stock data, then you can do it from there. If not, then there are some other indirect methods, so using satellite imagery or GIS maps, or if there have been studies where people have used the advanced imaging technologies like lidar and all. So this light detection and ranging, this lidar is very interesting technology, because using this lidar thing, one can develop the 3D model of a particular region, but it is quite expensive, so that is the constraint there. Or then there are different other technology methods which have been proposed in the literature, like shadowing calculation. These days there are a few things coming up with machine learning and things like that. Or then doing some micro level simulations and extrapolating it to a larger region. So there are a lot of technologies, a lot of different techniques which are available and which have been discussed in the literature. And it won't be possible to cover everything in this one lecture, but we will cover here four different case studies, four different you can say samples of techniques or methodologies for estimating the rooftop PV potential. And these different four techniques which we will be discussing, they are from different regions and from different backgrounds, and they pertain to different data availability constraints. So it will give you an overall picture of the different methods which can be used for this rooftop PV potential estimation. So the first technique we'll start with, this is one of the initial papers published in this area in around 2008. And this was done by a team of researchers from Europe, Asst, and they have actually focused on building stock data and GIS. So this is one of the earliest papers, and the good thing here was the availability of the data in terms of the building stock data. And because they had the details of the building stock in that particular region and the details of the buildings, so that's why they were able to go ahead with this method. So this gives you an overview of this method. And as you can see, this let's spend a few minutes to decipher this block diagram here. So because this block diagram gives you the methodology which they have deployed for rooftop PV potential estimation. So as you can see, there are three different sections of this block diagram. The top section talks about the physical potential. Then you have the geographical potential in between, and the bottom one is the technical potential. So first, they have started with the physical potential, which basically corresponds to the radiation availability. So they have taken the horizontal irradiation data from some of the standard databases and the Meteor network, and then using some appropriate practical numbers for the clearness index and the other reduction factors for the irradiation, they have finally arrived at the GHI, or the global horizontal irradiation, which they are calling as the physical potential. Then there is the geographical potential. Now, because this entire thing doesn't translate into the output, so there is this geographical potential is what depends upon the building information. So this is very critical here for this method. is that one needs to have a detailed building data for the entire region over which one is concerned. So if you want to estimate, let's say, the solar PV, rooftop solar PV potential of a city, you need to have the accurate building data for all the buildings in that particular city. And then the land use types and the building information and all that they have coupled with the irradiation values, and with developed some models to get the how much is the actual irradiation on the rooftop. And then finally, the last or the third stage is the technical potential, wherein now this initially you got the actual GHI, the global horizontal irradiation, which is there. Then from there you reduced it to how much is the horizontal irradiation on the rooftops. And from here you finally want to get the power generated output or the power output, which you can expect energy output from the PV modules. So for that, they have assumed some particular type of PV arrangement and taken some PV models with the models for performance, PV performance and losses and all. And finally, they have arrived at this power generated by PV modules. So this is the overall thing. But here, the most critical aspect for this methodology to be implemented is this building information. So until and unless one has this building information, one cannot really go with this method. So this is an overview. Let's now look at the details of this method, what they have done. So this is the region which they have considered for doing the your building for doing the analysis for rooftop PV potential. So any quick geography quiz now here. Can anyone identify which is this region? Which region this map belongs to or indicates which particular region? So this is the actually a little hint here. As you can see, this is Madrid here. This is Barcelona. So this is Spain actually. So this study is Escuero et al. They these are a group of researchers from Spain, and they did this study for the entire country of Spain. And what they have done here is that, as you can see, this is the color coding given here. So they have divided the entire country, the total municipalities, some 3,000 odd municipalities which are there across Spain. All the municipalities they have categorized as per their building typology and the population density. So in terms of the what type of building typology is there and what type of population density is there, based on that they have classified the different all the municipalities in Spain. And then this table here sort of gives you an idea about the details of the buildings which they have got there. So this is the building density and the population density. Based on that, they have classified it into different types of municipalities. Then the total number of municipalities across Spain, that they have around 8,000 municipalities that they have classified into different categories here with respect to the data available. And this is the total population spread across these different municipalities. And then there are a lot of different factors, as you can see here. So the urban area is this given here. How much is the urban area in kilometer square in each municipality? And then there are different coefficients which they have taken to as the reduction factors for getting at the actual available area. So this is the urban area, which is the total area under the municipality. And finally, this AA is the available roof area. How much is the roof area available per capita in terms of the active area on the rooftop, which can be used for PV installation. And for estimating that, they have for deducing the AA from AU, they have taken these different reduction factors: the void fraction coefficient CV, the shadowing fraction coefficient CS, and the facility coefficient CF. So there will be some because there will be some void area which will not be there on the roof. Then there will be shadowing due to adjoining things, and then the facility coefficient in terms of the competing uses of the roof area. So these numbers, these three columns here, those are the critical columns for estimating the area, and that they have done from the building data. So as I indicated in the previous slide, that this building information is the key to this method. So they had this building information for across the municipalities, and based on that, they were able to estimate these reduction factors, and then finally come to the available area and available area per capita. And based on that, they have done they have assumed a particular configuration of PV panels and the PV system, and based on that, they have finally come up with the final potential in terms of the energy output per year. So gigawatt hour per year, as you can see. So across all these municipalities, they have been able to identify how much is the achievable potential of rooftop solar PV in terms of the energy output per year. So this is the type of thing. So this is one type of methodology which has been developed for if you have the building stock data available in detail. But as I said, this is the also the you can say the drawback or the loophole with this method is that if you don't have this detailed building stock data, then this method can't be really implemented. So this is one thing. Then second method, which I just wanted to showcase to you, is something which uses the LiDAR, and LiDAR is quite an advanced imaging technique, light detection and ranging, and this is a very interesting thing. So you have LiDAR cameras which can be which need to be taken in some either through a drone or through some aerial device, and that LiDAR camera through the aerial device, this can be this can be taken up across the region where you want to develop, which you want to study. And then what the LiDAR does is that it develops a 3D model for that entire region. So if you fly this LiDAR camera over that particular area of concern, region of concern, then you can develop a three-dimensional model of the particular area. So, and once you have this 3D model, then it becomes very simple. Then you can just simulate this 3D model in some PV simulation software, and then you can estimate how much is the photovoltaic yield and the potential and all. So this method was, I mean, there are different variants of this. This is just one of these. So LiDAR and GIS and such things have also been used extensively. And this was published in 2013 and used for a particular city in US. This group of researchers, Jakubek and Renault, they did this for a particular city in US. And so these are the, as you can see, the methodology involves, first of all, it begins with the LiDAR data. And using that LiDAR survey, what they do is that they develop a 3D model for the entire city. Then they have done some hourly simulations. Any of the PV simulation softwares can be used for this purpose. They have used this Radiance or DaySim software. And using those hourly simulations, they have estimated the photovoltaic yield. And then the useful rooftop area also they have determined by the GIS tools. And using the GIS, the geolocation of data from GIS to radiance simulation model. So basically, the GIS thing has given them this rooftop area, and then they have mapped it onto the 3D model and the this radiance simulation. So using that, they have finally come up with the map of the entire city, which shows the PV output for the different pockets of the city. So this is what the thing, few images from this paper. So this is the particular area of the city, which this shows the bird's eye image, and then the LiDAR camera has been flown over this area, and using those LiDAR sensor, they have developed the this particular LiDAR point data, and then appropriately modified it to come up with this 3D model. So this final 3D model, as you can see, it very nicely and accurately represents the bird's eye image. And this particular 3D model can be used for your simulation. So they have used that 3D model for the simulation in the Radiance or DaySim software. And using that, they have estimated the energy output across the year. So as you can see in this graph here, for different days across the year, how much will be the energy output. So that type of simulation they have conducted, and then they have also got some measured data from some of the data points across the city. And based on that, they have, and the second thing, as I said, was the GIS thing. So they have also done this geolocation of data from GIS and estimating the rooftop area. So once you have the 3D model, you can obviously estimate the rooftop area and you can correlate it with the your 3D model and the radiance day sim simulations. And based on that, what they have developed finally is that this type of the detailed roof model for the city. So this thing was, I mean, till few years back, at least it was available as an online tool. I'm not really sure if it is still available. So for city of Cambridge in US, this one they have in Massachusetts state. So they have done this one, and based on that, they have developed this type of a solar tool, online tool for seeing, looking up how much is the solar PV potential in the different pockets of the city. So this is another example here for the PV potential estimation. And now we come to the third case study here, which is different from the previous two. And this was done here. This was actually a part of my PhD work, and which I did with my professor, Professor Rangan Banerjee at IIT Bombay. And this one here, we now in context of India, now the situation was different because so one thing is that we don't have that type of building stock data, the detailed building stock data which I showed you earlier, which the Esquerdo et al. Did for Spain. So we don't really have that type because our cities are not really planned cities. They are more like, as come up in a very organic manner from scratch, but without much planning and all. So even that type of building stock data details are not available, or even if they are in municipal records, some of those, but they are not really accessible or available for research and that type of analysis. So the availability of building stock data is a problem in the Indian context, which is not really readily available. And another constraint which we took upon ourselves was that if, let's say, we don't want to use expensive technology like LIDAR, we only want to go with the data which is available in the public domain, then how do we develop the estimate of PV potential or rooftop PV potential of a city? So with these two constraints in mind, we embarked upon this problem. And so our focus was that we only want to use the public domain data, which is available in public domain, and use some secondary methods for doing this type of analysis and developing a method for estimating the rooftop solar PV of a city in the Indian context with the data availability constraints of the Indian context. So this graph here, this figure, this map which you see here is the map of city of Mumbai. And as we understand, Mumbai is a huge urban conglomerate, and there are different other satellite towns and things like that. So this study was restricted only to the MCGM area, so the Municipal Corporation of Greater Mumbai. So this area which you see in this graph is just the area pertaining to the Municipal Corporation of Greater Mumbai, which is divided into 24 wards. So right from ward number A, B, C here, starting here in the south, A, B, C, D, E, so on, and up to T. So these are the 24 wards of the Municipal Corporation of Greater Mumbai. And we wanted to study this particular area with the existing data available in the public domain. So before we go ahead with this thing and I discuss how we did this and the methodology we developed for this is just some terminology which I'll be using again and again in this thing for discussing this. So just to clarify this. So there are few terms which we have defined. One is the PV available area, which is indicated as PVA. Then another is the BFA, or the building footprint area, and this figure here is just a schematic, simple schematic, just showing you the idea about these numbers. So this bigger rectangle here, the biggest rectangle actually in this figure, the as you can see, this one I'll just highlight. So this big rectangle here, this is the plot area of, let's say, some particular plot. So this entire thing is the plot area as it shows here. Now in that plot, as we understand, there will be some open space. So this white space here, this is the open space, and this is the building footprint area, this BFA. So the two shaded rectangles, the dark shaded and the light shaded rectangle together, this is the building footprint area. So in a given plot, the building is there for across a particular area, and there is some open space. Now, in this building footprint area, whatever is the footprint of the building, not entire thing. I mean, first of all, there'll be some reduction. There'll be some, like if we look at the terminology from the square paper, there'll be some void fraction. So there'll be some portion of the building footprint which will not translate into a roof area. And then even if some it's translating to the roof area, no, the roof is available, then also there'll be some facility coefficient. So the facilities on the top of the roof, like your maybe the solar water heater or the water tank, or some other utility area, those will be eating up some space. And then after that, whatever is the available free space, that also there will be some area which might be shaded, so there might be shadowing from adjacent structures on the roof itself or from the neighboring buildings or trees and all. So removing all these three, removing that void fraction and the facility fraction and the shading area, what finally you get is this PV area. So the PV available area, PVA, that is what we are defining here. So, and in this also we accounted for the module row spacing and all, which will be needed for shade-free panel till 21st of December of each year on the winter solstice. So finally accounting for that, what is the active area? What is the PV active area of the panels which we can install on the rooftop? So this is just a schematic. I mean, these the areas of the rectangles are not to scale, or they don't represent any ratio here. This is just to explain the terminology. So the idea is that in a given plot area, there will be some reduction and there will be some building footprint area. And then from that building footprint area, we'll be having some PV available area. And we define these two terms also. So one we defined is the BFA ratio, which is the ratio of the building footprint area to plot area. So BFA over plot area, BFA by plot area is what we defined as the BFA ratio. And the PVA ratio is the ratio of the photovoltaic available area to the building footprint area. PVA by BFA is the PVA ratio. So this is just some terminology because we'll be using this. Now this figure here, this gives you the methodology which we developed here, this block diagram. This gives us the methodology which we used or developed for estimating the rooftop PV potential of Indian cities. And here there are three, you can say there are four blocks. One is the area estimation block, which is the most critical one in terms of estimating the PV active area on the rooftop. Then second is the insulation estimation block. So how much is the radiation available? And then third is the PV device and system block. So what type of PV system and configuration do we take for that? And taking all these three into account, finally, what we get is the technical potential and the generation profile and the capacity factor expected. And this then we also compared with the existing energy requirement and consumption scenario. And this is what the results and analysis block is. So here these four are the important, the different things, but the most critical one here is the area estimation block. This is where the critical thing lies. So for a huge city like Mumbai, how do we estimate that what is the available rooftop area, PV active area, which is possible in the entire city? So as you can see here in this block, the top area estimation block here, what we did is that we used satellite image samples, and using those satellite image samples and GIS tools, we estimated the building footprint ratio. And that building footprint ratio was done for across the Mumbai city. And finally, what we arrived at was the building footprint area. And now for estimating the PVA or the PV available area from the building footprint area, we took some values from literature or for the different areas. And also we did a lot of simulations in the PV-Syst software, which is PV simulation software for the, the micro level simulations for some sample buildings. And finally, we arrived at an estimate of the PV available area. And the insolation estimation, the irradiation, this actually we just use the standard. There are different models which are available. We use the isotropic model, the Jordan model, and using that we estimated how much is the plane of array irradiation. And then for PV model also, we used some of the standard PV performance models, and based on that we did the analysis, and we finally came with the output. So this is what the methodology is about, and just some glimpses of the thing we'll show to you. So like, this entire Mumbai city, across Mumbai city, we took different samples of buildings. So, what we used here as the starting point was the land use data of the Mumbai city, which was made available by the Municipal Corporation of Greater Mumbai. and that they had released in the public domain itself. We got the different land uses and subcategories of land uses. And across those different land uses, we took some different number of samples of these different types of buildings. So for residential, commercial, industrial, and so on, for different type of land use types, we took some sample buildings from different wards of municipal corporation. And what we did is that for these sample buildings, we analyzed them from the Google Earth imagery. We got the GIS maps, and we did the geotagging and the location of these different maps, and we estimated the rooftop area and the PV active area for these different sample buildings. And so the results for this from this particular thing, from these taking these samples across the city, we arrived at some numbers across these different land use categories, and we averaged it out to get this building footprint ratio. So as you can see, the overall, all the land use types are listed here in this table on the left hand side. Now in each land use type, there are different categories and subcategories, and not all categories might be permissible for PV installation. So what we did is that we did some survey, and we zeroed down on the permissible subcategories in each land use type. What are the possible categories and subcategories where we can expect to have a rooftop PV installation? And for those permissible subcategories and categories, what we did is that we did that type of GIS analysis for the sample buildings across the city, and from that we estimated this mean building footprint ratio across these different permissible subcategories. And then for these sample buildings which we had chosen in the first step, for these sample buildings we did the analysis in the PVSys software, which was really time taking because we had to develop 3D models like this. So this is like for one residential building here. So like that, we developed 3D models for different buildings, and simulated that in the PVSys software. And using that, we got the reduction factors for the PV available area. And we took a very conservative estimate because it's always good to be on the conservative side in such studies. So we took the P95 value for PV available ratio. So for across these samples which we took across the city of Mumbai, at least 95% of the times we found the PVA ratio to be 0.28 or above. So it's not the mean value, rather the P95 value which we took. And so using this analysis, these were the results which we got for the area. So this was the total available area under the Municipal Corporation of Greater Mumbai. And from that, we reduced down the building footprint area using the GIS and the techniques for the sample buildings. And then using the PVSys simulation for the sample buildings and taking P95 conservative estimate, we arrived at the PV available area. So that was the area estimation, and then this was the most critical part of this. And then we also did the insolation estimation, the radiation. For this, we didn't really develop our own model. We just, as we are aware, as you might be aware, that there are different transposition models which give us the the plane of array radiation. So we just used one of the simplest and the isotropic models, which is known as the Liu-Jordan model. And using that model, we estimated the plane of array irradiation in the plane of tilted PV array. And we used the Asht database for solar radiation for this. And using this, these standard numbers, I mean, for the different solar angles and all, and the local latitude and tilt of PV array, same as the latitude. All these different things, taking these different standard numbers, and using the 2009 Asht handbook climate design data as the base in terms of the irradiation and the temperature data, we arrived at the irradiation. And then finally these set of equations, they are just the standard PV performance model for the output of the PV in terms of accounting for the power temperature coefficient. So we used these different models for estimating the panel temperature and the cell temperature, and then accounting for the PTC, or the power temperature coefficient, and the actual PV output under the realistic conditions of different temperature loading across the year. We did the simulations in PVSys, and we used standard the polycrystalline module. At that, now please remember that this study was done in 2014-15. So The efficiencies we took on a conservative side as the 14.5% as the mean efficiency. And using that simulation and all, using these three components together, finally we arrived at the technical potential of rooftop PV in Mumbai city. And this is what the result comes out to be. So what we found as a result of this study is that in terms of the installed capacity which we can expect in Mumbai city or for MCGM area, we estimated that the estimated technical potential in MCGM area for rooftop PV is around 2.1 gigawatt peak. And in terms of energy output, this is what it will translate into with respect to the monthly rooftop PV generation across the year. So the units here are million kilowatt hours or million units across the year. So this type of thing we sort of estimated from this study, and these are the numbers showing the monthly capacity factors for a rooftop PV installation in Mumbai city. And as you can see, the numbers are somewhat on the lower side because of the value of the rated PV panel efficiency, which we took only as 14.5% with respect to the polycrystalline silicon panels available around that time. So now with increasing advances in the PV panel technology and much higher efficiency panels being available, these numbers will definitely move up, and so will be the output also. The PV output will be higher as the PV efficiency matches or improves with the ongoing research. So this is keep in mind that this is with the rated PV efficiency of 14.5%. This is with that value we got these numbers. And and then we did some analysis in terms of so in this graph here, as you can see, the first graph which I showed you, this one is the expected output with 14.5% efficiency, median solar panel efficiency, which was there. And this third graph here, this shows the comparison, because the lower bound of this graph, this lower bound, this particular line or this particular curve is with the 14.5% efficiency panels. And at that point of time in 2014-15, the maximum the commercially available maximum PV efficiency was around 21.5%. So this top curve here shows the output with the around 21.5% efficiency, which was the maximum commercial efficiency available at that point of time. So what we estimated is that the actual PV output, actual rooftop PV output of Mumbai will probably lie somewhere in this range between this median efficiency and the maximum efficiency. So this we called as the most probable band of solar PV generation for Mumbai city if we use the entire potential. So that is the output we got here. Then this curve here, this graph shows the daily rooftop PV generation. As we understand, as I said, that the daily profile of solar radiation is having this type of parabolic nature and peaking in the afternoon. So this graph here just shows you some comparison in terms of how much is the daily output we can expect from the rooftop PV scenario of Mumbai. And the black curve is the annual average, whereas the top dotted curve is the month with the highest solar irradiation, which in case of Mumbai comes out to be month of February. The data for Mumbai showed that irradiation was highest in February, whereas the lowest one, the dashed one here, this was for several months. In fact, it was around this value. So in fact, for June, July, September, and October, for these 4 months, almost it was close to this value. But the least one in terms of the absolute values was October actually. So this is that type of variation we found over the day for the radiation out for the PV output. And then we wanted to see, putting it in context with the existing demand of Mumbai in terms of the power demand, where does this all lie? So this was very interesting to see. If this study was done around 2014-15, so we had the annual the electricity demand data of 2013. And as you can see here, this graph here, this is the monthly demand of Mumbai city in year 2013. So, and this is where our expected rooftop solar PV generation lies. So as you can see, it's a much smaller fraction of the overall demand. And so for a big city like Mumbai, we can't really expect a very large share. But yeah, at least what we can expect is that with this type of rooftop PV generation, the peak will be coming down by some particular fraction at least. So this is what we got for Mumbai city, is that this was the monthly demand over the year, whereas this is what is our expected band of PV output from the overall rooftop PV potential of Mumbai. However, this needs to be mentioned here is that this is just a comparison. The demand here which we show, which we see in this top graph, this is the demand across the year for all the hours in a day. But as we know, this PV which we are showing here at the bottom of this graph, which is being generated from rooftop PV output, this, as we understand, is available only for few hours in a day, so only for the sunshine hours. So what we thought is that, I mean, this is just in comparison in the absolute terms across the all the hours taken together. But what if we look at the specific hours? So what if when the sun is there and the PV is active, and in that time, how much of the demand of Mumbai can this PV meet? So with that particular idea, what we did is that we did this type of analysis here, and this gave some interesting results, as you can see. So the daytime, the time when the sun is there, that time, as per the Maharashtra Electricity Regulatory Commission, there is some time of use tariffs for the industrial consumers. So using that as the base, what we did is that we classified the overall daytime into three categories. One is first is the morning partial peak, which is from 6 a.m. to 9 a.m. So during this time, from morning 6 a.m. to 9 a.m., what we see here in this graph, this is a little crowded, but I'll just guide you through this. So left-hand side, the left axis, as you can see, that vertical left axis is the percentage share of PV, and right-hand side is the demand and generation values in the million units. So which are in the line units. The lines are, the axis for all the line graphs is for on the right hand side, and the axis for all the bar graphs is on the left hand side. So so all these bar graphs which you see, those are the percentage share of PV, and the axis for that is here on the left hand side. So in this graph also you can see, the bar graphs also, there are two. One is at the highest efficiency, that means 21.5% rated PV efficiency. Second is at the median efficiency, which is the 14.5% rated PV efficiency. So even if you take this one at the median efficiency, the light bar graphs, you see here that the percentage share of PV in the morning partial peak is, as you can see here, it is going in this particular range. So it is as low as around 7% or so in few months like January or August, September, October, and it peaks to around maybe around 12 or 13% in the month of April or May. So in that range, from 7% to 12% across different months, this much share of the morning partial peak we can hope to mitigate by having the rooftop PV generation. But so this is for the morning partial peak. But then interestingly, if you look at the numbers for the morning peak, now the numbers are very different. So the morning peak, as per the MERC guidelines, is from 9 a.m. to 12 noon. And during this time, 9 a.m. to 12 noon, as we understand, is the time when the sun really peaks up in the day in the sky. So here again, if you see the percentage share of PV, and let's again take that same panels at the median efficiency of 14.5% rated PV efficiency. Now you look at the numbers, they are very different. You see, this is the range now we are talking about. So now even in the worst month like June, July, August, September and all, the ratio is around 30 to 35%. So around 30 to 35% of the demand in the morning peak hours can be expected to be met from rooftop PV, even in the rainy season months. And in the non-rainy season months, when the sky is really clear, so like if you look at Monday, the January, February, or November or December, the value is much higher. It's typically in the range of 55 to 60%, and the highest is for February. So in the month of February, around 60% of the morning peak can be mitigated by the PV, the rooftop PV potential. So that type of, this was interesting, that though the overall share of PV in the overall generation mix of Mumbai can't be really very high, it will be low overall, but during the morning peak hours and in some of the months, a very significant portion of the demand can be met by PV. And same way, this was the third slot as per NERC, the afternoon partial peak from 12 noon to 6 p.m. And this was in between. So the results for the share for of PV in the afternoon partial peak is in between the morning partial peak and the morning peak. And here again at median efficiency, as you can see, the percentage share of PV is ranging in the range of its least in the month of October at around 25% and highest in the month of February around 35%. So in that range from 25 to 35% of the demand in these hours, afternoon hours, can be from PV. So this was the detailed analysis which we did for Mumbai city, and tried to put it into context in terms of how much will be the impact of this on the generation mix and what to expect in terms of the rooftop PV potential of Mumbai city. So this was one study which we did in detail. And recently, we tried to extrapolate it to some other cities of country also. So this is one recent paper which I just published this year and 2020. And here what we did is that we just tried to extrapolate the results of Mumbai city to other cities. And here the intention is different. So let me just clarify that. That's why the name of the paper also, as you can see, it talks about approximate rooftop solar PV potential. We are not. So this paper, this is like the fourth case study which I just wanted to highlight to you, is that no, the previous three which I showed to you, the Squardo one, the Jacobic Renard, and the Mumbai one, those were the detailed rooftop PV potential studies, where the authors or researchers, they developed detailed methodologies for doing the exact PV potential of the region. But this fourth one is of a different nature, and I put it here just to showcase that sometimes maybe we don't need that type of detailed analysis. We just want some approximate results. And the application of this might be in high level renewable power scenario planning. So suppose I want to do the generation expansion planning of a larger region, or for the entire country, or for one regional grid, then I don't really want to look at the nitty-gritties of the details of the PV potential of each city or how it is being done. But I just want some first cut, or the approximate numbers in terms of what to expect in terms of the order of magnitude. So this paper is with that particular intention and with that flavor. So here the focus is on developing a workable estimate of PV potential of a region, rather than going into the details and the exact PV estimate. So this one here, what we did is that we used the results for Mumbai city, which we got earlier in the previous paper, as I showed to you, that those Mumbai results we used as the base results. And we used just some extrapolation. We developed some extrapolation methods for extrapolating the Mumbai results to a lot of other Indian cities. So this is the graph, the block diagram here on the bottom right gives you the methodology. So what, as you can see, the methodology, what it does here is that the building footprint area and the PV area, those were the two critical variables in the previous methodology. So we just developed some correlation methods for extrapolating this building footprint area to a larger to other cities, and then some particular trends we observed in terms of the PV available area, how it varies with the latitude and the shading factor and all, how it varies with the latitude, and we just developed those extrapolation factors and used it to extrapolate the rooftop PV potential of the other cities of India. So we didn't go into the detailed land use data and the details of each of these cities. We just developed the extrapolation factors and using these factors, extrapolated the results of Mumbai to the other cities. So this study we conducted for 13 of the largest Indian cities, having population of more than 2 million each. And the total population across these 13 cities is around 79 million. And what we found is that the total technical rooftop PV potential of these cities across these 13 cities found out to be around 17.8 gigawatt peak. So I'll just give you an quick walkthrough through this one and just show you some typical results. So one of the extrapolation factors regarding the building footprint area. So here we consider two things into account. One is the intrinsic relationship between building density and population density, and that's quite understandable also by common logic also, that as the population density will increase, typically there'll be more buildings which will be needed for the different uses, for residential, commercial, industrial uses and all. So typically it is expected that with increasing population density, the building density would increase. But that is just one factor. Another factor is that the vertical growth of the cities is also something which is important. So some city might be having a lot of vertical expansion, like many tall buildings like Mumbai and some of the metropolitan cities like Delhi, Mumbai and all, they will have a much larger vertical profile. Whereas some other cities, tier 2 cities and tier 3 cities, well, will not be having so much vertical expansion. They will be having more of a horizontal spread. So what we did is that we took these two factors into account. One is the relationship between building density and population density. And using that, we developed we got some, fitted a regression model and got some building density results for these different 13 cities. And another thing was the correction factor. So we developed one correction factor for building density, taking into account the vertical profile score of the cities. So for this, we used some databases of the different cities, and we considered how much is the the vertical spread of the different cities. So the higher the vertical profile score means the city is having much more high rise buildings and skyscrapers and all. So there was a scale for this, and some of these cities are having very high scores and are having a much taller vertical spread, whereas some others might be having lesser values and lesser vertical spread. So based on that, what we did was that we used this vertical profile score we used for developing some building density correction factors, because as I said that though population density the building density is expected to rise, but if the vertical spread of the building of the city is more, then this building density won't rise in a very proportionate manner. So that is the correction factor here. So using that correction factor, we arrived at the final building density numbers for these cities, which were used for estimating the building footprint area. And so these were the results which we got for these different 13 cities. And then the second aspect is the PV available area, how it varies across the different cities. So for PV available area, what we did is that we took different building clusters. So these are the 8 different building clusters which we took, which are like sample neighborhoods. Because the PV available area will depend upon the interaction of the buildings. How much is the shadowing, due to the adjacent buildings. So we did some survey across different cities, and we arrived at some of the typical building clusters where the relative heights of the buildings and the relative gaps or separation between the buildings we changed, and we arrived at these different 3D building clusters, and we simulated these building clusters across different cities. So we took 5 cities for this case, for the analysis, for the PV analysis, for this PV simulation analysis. We took these 5 cities, which cover typically the entire length and almost the breadth also of the country, from east to west and north to south. And so for each of these 5 cities, we estimated, we did this PV-SIST simulation for these sample building clusters. And using that, we estimated that how much is the change in the PVA to BFA ratio with respect to that of Mumbai, because Mumbai is our base case. And another thing we studied is that the shading factor, the shading factor, how it changes. So these are the different building clusters, the 8 building clusters which we took. So we did the simulation for all the 8 building clusters across these 5 cities. And using those results, we estimated how much is the change in the PVA BFA ratio and also the changing in the shading factor. And finally, taking into account these things, we estimated that how much is the PV available area, how it is expected to change across the country. So please remember that this is an approximate analysis, and the actual numbers will be different if we take much more detailed local factors. But here the idea is to just get the approximate numbers for a high level analysis. So using that, we got these different potential for these different 13 cities across the country. So the map on the right hand side shows the same numbers in a proportionate manner on a map, and the table on the left hand side gives you the actual numbers of the estimated rooftop PV potential of the different cities. And the total, it adds up. If you add up all these 13 cities, what you get is around 17.8 gigawatt peak across these 13 cities. So this was one another type of case study where we did the approximate rooftop PV potential using the extrapolation factors. So this completes the 4 case studies which I wanted to showcase to you. And there is a lot more going on in this area. These are just few samples, and there are several other papers and interesting research which has been done in this area. But if we look at the way forward now, so because this thing has been done a lot many times, the PV potential estimation and the research related to this is almost now more than a decade old, and there are a lot of existing technologies and methodologies which are there. So not much new things in terms of the developing the methodology, but there are these few things which are really interesting and which you might be interested in looking up in the future. Is that one is there is an increasing trend of applying machine learning techniques to the estimation procedure, and that throws up some interesting opportunities. Then there is another thing is that now, because PV potential estimation, whatever we discussed so far, and most of these papers they talk about technical issues. So now there is an interesting and more research also towards the third dimension, or the achievable or the market potential, for which one needs to understand the policy and the social issues and the behavioral aspects and all. So there's a lot of increasing focus towards the implementation issues in terms of the policy and the social issues. And also there is an emerging concept of near zero energy communities, not exactly net zero, but near zero. So those are also being explored, and how those things can be designed for an urban landscape and all. Those things are also being some interesting things which are being taken up in this particular domain. So this completes my presentation, and thank you everyone for your patient listening, and for this interesting opportunity to discuss the things. So it's open to questions. I see there are few questions which are already there, and other participants can also put in their questions. So organizers, should I take up the questions, or anything I have from your side?
Yeah, we'll give it. Thank you, sir. Thank you for your very detailed and informative session on solar PV potential estimation for planning of renewable energy scenario. We have started with the basics of solar PV potential, technical potential estimation with respect to rooftop solar PV generation. Then you explained the various methods for rooftop solar PV potential estimation, like building stock data plus GIS, LiDAR, GIS plus hourly simulation, land use data, GIS micro level simulations. This session is now open for discussions. I would now read out the queries posted by some of the participants. I guess there are 2 general questions are there. So one is asking, what is the actual generation by solar PV in India?
Okay, so yeah, so in terms of generation, actually the numbers might be lesser, but if we look at the installed capacity, it's really promising. So you might be aware that this National Solar Mission, we have a target of 100 gigawatt peak by 2022. And out of this 100, there are 2 categories. One is the utility scale solar PV, which has been given a target of 60 gigawatt peak, whereas the rooftop segment has been given a target of 40 gigawatt peak. So the latest numbers, I mean, MNRE keeps updating it every month. So a couple of months back or so, when I looked at the data, what I found was that the utility scale PV is really catching up good. And out of a target of 60 gigawatt, roughly around 32 gigawatt peak is what we already have installed. So which is very impressive. But in terms of rooftop PV, the growth is really sluggish and it's very lagging behind. So in terms of rooftop PV, out of a target of 40 gigawatt peak, we have somewhere around 2.5 gigawatt peak only so far. So it's much lesser, and the growth is also very slow. and so that is like in terms of the installed capacity, but the generation, if you talk about the energy generation actual, then those numbers might be even lesser. I don't have the data right now for solar PV, but overall when I looked at the in terms of the renewable share in India, what I found was that the overall renewable, all the renewable technologies taken together, the share in the installed capacity was around 12%, whereas the share in energy generation was only around 6%. And that is always usually true for all the renewable technologies, because as I discussed, due to the resource constraint, the capacity factors for renewable energy technologies are usually much lesser than fossil fuel technologies. So those are a few insights on that.
Okay, sir. One more question. What is the effect of unanticipated degradation issues on potential estimations?
Sorry?
What is the effect of unanticipated degradation issues on potential estimation?
That's very interesting, actually. Yeah, so degradation of the modules across the life of the modules is something which, yeah, this is really an important topic from the practical consideration. And there is a lot of, people who have been doing some research on the PV reliability aspects and the degradation of the modules over its lifetime. So the actual numbers, in fact, we don't have really many of installations so far in India which are that old, but few of those might be there. But what we did for this study was that we just took some standard numbers. So we took some numbers from literature. So as far as I recall, around 0.5% to 1% reduction in the PV output per annum, that type of things we took. But the actual degradation numbers might be different. It will also be very much dependent upon the climate of the place. So I think that might be something which can be explored further.
Okay, sir. Thank you. So one of the participant is asking how the efficiency of solar PV plant is estimated.
Yeah, so when we say the rated efficiency, as I discussed, the rated efficiency is usually given at the STC conditions, but that rated efficiency is pretty, optimistic in nature actually. And also, if you talk about the overall, because the question says about the overall solar PV plant, so there the power conditioning unit will also come into picture. So, I'll just come back to this same equation. So the efficiency of the PV, the rated efficiency, that will be there. So which might be in the range of 18 to 20% with the present technology. But then there is the power conditioning unit efficiency also. So the inverter and the associated power electronics, which is there, those are pretty efficient. But then we take the year-round efficiency, taking out into account the different weather conditions and all. So this also, typically, even if you take a conservative estimate, 85 to 90% is good enough. So accordingly, the numbers can be worked out. But the important thing to be kept in mind is that this number, especially this eta PV or the rated PV efficiency, this is very, very subjective number, and it is very much prone to fluctuation due to the irradiation and the temperature effects. So the actual numbers will vary. The rated efficiency might be in the range of 18% or so, but the actual numbers would be different. Yeah.
Okay, sir. Thank you. Thank you so much. Is there any queries by the participants?
Dr. Rhythm, Vivek here.
Oh, hi Vivek.
Yeah. I have a casual query. Actually, if when we are designing a community-based grid, suppose a PV-based community grid, then the nodes to be designed, we are assuming these nodes are very nearby, in maybe in a square kilometer area. So at each node, if different panels are installed, then do we need to assume irradiance differently for each node, or can we assume it as same? If it's
Okay.
yeah. From power system point of view, whether it will affect the nodal power injections or not, that's my
right. Yeah, and so I think Vivek, what I have, I was working a particular aspect. We have been also looking on the solar resource variability and fluctuations. So what we understand is that in terms of the long-term power projection, it will actually not vary much. In fact, the most of the databases which are also available, they are of a range of, the spatial resolution is 10 kilometer by 10 kilometer. So if you talk about a resolution of 1 kilometer, definitely when we do the planning, we take the same radiation value. But there, the constraint would be different, which would be mainly about the solar fluctuation at a smaller time scale, radiation fluctuation. So that might have a important impact on the small scale solar PV. So if you have a small solar PV panel planted at different, some few panels planted in a 1 kilometer grid, as you're saying, across this thing. So those fluctuations will cause some, the radiation fluctuation will cause the sizable voltage fluctuations across those small PV installations. But if you take the overall thing, there will be a geographical smoothing which will come into picture.
Okay. So in long term, it may not affect.
No,
There
not
won't be
really.
any considerable effect.
No, not really. In fact, that type of fluctuations can be easily taken care by the interconnection hardware itself.
Okay.